We're going to do a quick review just of notebook number 5, and then we're going to finish. We stop at multi-categorize and then the full example of notebook number 5, and then we're going to go to notebook number 3. I did add notes based on all the comments that we have on the previous session. So now I'm going to post this particular notebook, which all the notes are marked with walkthrough notes. For example, in here, we said that default X was very important because it will allow us to do the automatic library descriptions when you have also I added a link so we can go and do those. Okay, so what we saw last time in this notebook was basically the transform. We were doing 3 things. Think of the data set that you're going to process. What are the 3 actions that are most important, which are get your data set, that could be images, data frames, and then be able to split it into training and validation, and be able to label your white object, right? Your categories. Be able to label all of those. So for get, we saw, for example, we talk about the private functions, and we saw just the horsepower of how do we go and read a directory in a system, or the get files. That usually for computer images is going to be just a list of every single image, it's a list of past. We may note that in particular, Jeremy may note that os.walk was really efficient. So that's what they did, that part here. That's why they selected this one. It can read a directory in seconds. We mentioned also that it's really important to do the test equivalence. We can look at the method themselves for testing. That's in the fast for part. So in here, in the first notebook, we're going to see all the different ways that we have to test. The most common one is just test the quality. Like in this case, just make sure that A is equal to B, which is the one we were using there. Like in this case, we downloaded the files. Well, we read the directory of the images of the class train and the class 7, and then we read it from the directory of train just to use different types of the recursive. If we put the full path, we don't need recursion. If I put it in train, then I need recursion because first I need to go to the class. And then we make sure that the number of images that we got on both are the same. So that's what we're using our test equivalents. Also, test equivalents are going to be part of the documentation. And if we don't want them to be part of the documentation because they're not interesting, we just hide them. If we don't hide them, then they're going to be part of the documentation. We talk a lot about this part that we're going to see it a lot. These functions, which called camel case, you're going to see them. The name is going to be always camel case, and it's going to finish in ER. That is a way of creating something that is very repetitive behavior if it's something that you're going to have commonly. So you want to create an ER function such that your notebooks are talking about this particular level, right? It's like a medium level layer. So you don't have to go and specify the same behavior every single time. For example, every single time you want to read image files, you don't have to go and check, oh, well, but make sure that I only root image section, right? So you don't want to, every single time that you're going to read images, make sure that you only pull the file that are images because the directory can have other files. So for that, what you're going to do is you're going to create an ER function that already has the part that is only going to be looking at extensions that belongs to images. So if you have this kind of repetitive behavior, that's what you're going to do. Such that it's more natural when you're writing. The same way that I'm going to have a getter, let's say for images, then I'm going to create another getter for text. That way, when I'm writing with text, I don't have to worry about the details because I can just reuse my functions if I have them already specified with these particular parameters. But we saw that most of them at the end were just using the internal function of get files. Another part that we saw that was important in this was functionality that Jeremy added for the store attribute. That just was a way of avoiding having to specify the parameters. Like in this case, we receive a bunch of parameters in here. We don't have to write a cell for every single time because sometimes we can receive 10 parameters. It's just a way of making this more efficient. So we can just say, store the attribute in this class. In what are the attributes are going to store? Well, I'm going to store this particular list of attributes. And it knows where it needs to store it, in which particular context of the class it needs to store it. We talk about split. The more common one we clearly saw is the random splitter. You just say a percentage of your test that is going to go to validation. And in here, what you are doing is you are creating the indexes that are going to be part of the validation, and which part is going to be part of the train. The interesting part in here, we saw that this is an object. It's a list object. It's a collection, also from FastScore. That is it's an improved type of list. It allows you to do some operations that the normal list from Python doesn't allow it to you. What else in here? Sometimes we see that we don't need to rewrite something that works. For example, he does have a method for train-time splitter that all it does is call the one from scikit-learn. So we can use stratify to make sure the proportion of the classes in our validation and our train are kept. So we don't have, and I really like that part. And he uses that then for metrics and for other parts that if that's something code that works, we're not going to re-implement it. We're just going to wrap it in it's what he did in this case. We just call the one that works here. So we saw the random splitter. We have the stratify splitter. Then we saw indexer, I believe is this, index splitter. In this case is when you already have something that tells you, you have a pre-selected the items that should belong to the test or validation set as opposed to train. And in this case, you just want to be able to separate them based on that particular flag. So for that, we use this index splitter. Notice that for that, another Python functionality that he added, this is not from Python, but this, which is doing 2 steps in one. It's just doing that given the length of a list, it creates the actual item. So this doesn't have to be in numbers, right? This could be a list of files. So given a list of files, it will create the indexes that belong to that particular list. So just create this particular list. If it's a list of 30 files, it will just create the list of the 30 indexes. So we can then process them and then look at how we're going to split them in here. Grandfather was just one particular that sometimes we know how to split our data set because that's how it's a common method. Like in the MNIST data set, the grandfather folder tells us whether it's trained or valid. So we can just read it directly from the directory structure on the particular path object that we have for each one of our items, like in this case. So we have the grandparent splitter that is just have this function over here, but like we mentioned, that will be the path for valid train. So we just go and read it and then we can split that way. So we have random, we have by specifying it with a flag, we have by using it, the folder structure in this case. In here is a function, and the function tells you whether or not you should be on the whether or not you should be part of the validation of the training set in here. We saw max splitter also that tells you just the value, again, whether you should be one or the other. The first is going to be the collection of items with the mask is false, and then the collection of items that is going to be true. Like in this case, you have, this was your original list, and then when you split based on this particular flag, then it's going to give you all the ones that are false, 1, 2, and 4, and the ones that are 3, so you can split them as train and validation. I saw this file splitted. It seems here that it was a typo. In this one, it seems that what you have is a file, that the file itself contains the lines of all the possible items. And then you specify, read this file, and then from this file, specify which part should be part of train and valid based on a particular function. It has an example here that the file should be 1, 3, and 4. So this one, so if you have this function that tells you how it should be split, then you can then make sure that you split based on this function. It could have been something that a regular expression that parses the particular name, if that's what you want to do. Column splitter is another way. In this case, you're reading a Panda data frame in which one column already tells you whether it's going to be part of the validation of the or the train. And random subset splitter is you want to split, but you want to make sure that you do it through subsets. So kind of continuing, you want to keep some sequence among the training and the validation. it's a random, but you're still keeping that particular, like in this case, you keep from 0 to 70 and 70 to 30. So you, in this case, you are just, like if you're doing time series, for example, where the order means something and you want to preserve that order. And you want to keep the same time validation separated from train.
So where exactly are you seeing the order in the code over there?
It's this part in here when it says,
because that's a random perm, right? So basically what you're trying to do is just shuffle and then subset it out. There is no order as far as I remember.
Let me check in here. I think I remember that it was that these splits, let's see, split 0. That's the beauty of, you can always just look at how the data looks.
Because the whole idea of that function is to find a smaller subset of your bigger data set. And your algorithms will work and translate to your bigger data set only if it is randomly sampled from the original big data set.
What would be the difference then between this one and the random splitter? We actually have a random splitter.
Yeah, I think the difference is the IDs are sequential, not the values. So if you see the return IDs, they are from start to train length and then from train length to train length plus valid. So this indexes are sequential, but obviously the values returned would not be based on the.
So I'm returning the values, not the index. I was trying to return the indexes. Oh, it's here. Return the index. So
the value that is just being returned is continuous just because its IDs are in the same order. That's all, right?
Yeah.
Actually, the values are not sequential, right? It's just the index.
Exactly. Yeah, so it is keeping that sequence, right? The index, you're right. So the index of the thing. So you're keeping, if the rows, that's true. If semantically the rows represent the time series and that's how you have them, then the validation in this case would only be the rows from 70 to 100. So you are keeping the first 70 for training and the second set from 70 to 100 for validation. So this is different from the random. If you just wanted to take a subset, I can do my random split it and I can select the size, right? In here, I'm telling it preserve it. So don't randomly shuffle it and select indexes, which is what the random splitter was doing. In this case, keep the first 70% of the rows in my training, and the 30% of the second part of my rows are going to be here. So yeah, this is what I wanted to show, that the second part, this one is returning the validation of the index for the valid ones is going to be indexes from 70 to 100.
So again, I think the whole thing is shuffled, and then you're saying take the first 70% and last 30%.
That's correct.
If you look at the last but second line, IDXs, you're doing a rand perm there. So you're rand perming the whole thing. And then you are taking the first 70% as training and last 30% as, or I mean, then you're doing that split. So that's why your IDXs are seeming to be in order. But that has nothing to do with the data being in the order, right?
That's a good point. I have learned that the indexes you first generated in a random permutation for the order.
So the difference, what you were saying between random splitter and random subset splitter, random splitter takes the whole data set and then randomly splits it into two parts. That is correct. In random subset splitter, there's another added part to it. The whole idea, if the reasoning why random subset splitter was put in was because if you have, let us say, 1 million rows, you don't have to always do your calculations on that, right? Jeremy's idea is that take a small subset and just do all your experiments on that. Now, why do you have to take a smaller, I mean, when you take the subset, the whole idea is that it should still be representative of your original data set. Only then whatever you run, even though you're running it fast, will make sense. So that's where both these things merge together, the random subset splitter.
Okay, thank you.
Yep.
And then labeling. The classic one, but just again, reading from the structure of the folder, parent folder. Notice that one thing that is interesting here, this is a function, and it's a function that doesn't return a function. So that's That's just a different way of doing it. Instead of having the camel case, ER, that returns a partial function. In this one, it's actually just giving you the value. We're going to see that the way that we're going to use them is going to be the same. We can use this function and that returns the value or a partial function as part of the transform, and it's going to have the same behavior. So this is very common when you need to extract your class or the label. You're trying to extract your Y value from the name of the file, that example that we saw on the pets, where you have the breed or whether it's a dog or a cat from the name. So you just have, you set it up, and then you have the particular regular expression that is going to extract what you need in there. And then we saw a little bit about the raw strings, which were, I believe was in here, or was it here?
Could you scroll up a little bit? What is that assert here, in cell 69, the second last line? What are you asserting there?
When you don't find, imagine that I'm looking for an expression. Let's just say here. Let me just open. Imagine that I'm looking for the name, and the name was cat underscore 55 PNG, right? In this case, I'm looking for a pattern. Maybe my pattern is that to look for something that has letters and then my underscore and then just numbers, because I know that all my images are just going to be numbered with the name in here. So I'm trying to get a regular expression that is going to retrieve this part of the name. But if this fails, because what I get, let's say that the file was actually called like this and without having the regular expression of the underscore, and I put the underscore as part of the regular expression that I'm looking for, then it's going to fail. And in this case, it's just making sure that it did find, in this case, the expression that I was looking for. And if I'm looking, if I did find it, then return that, and then make sure that you didn't not find it. That's what I believe it's doing. If anybody has a correction, that please go for it. But I think it does. Then I'm trying to, oh, should probably here. In this case, because we were doing some regular expression that was reading the name of the file, and here was using as part of the regular expression the separator, because it was actually reading, trying to read folders, like the parent folders. Then we were using what it was called a raw string, such that we can allow to use this particular separator. And it was also what it was what is called the F string, which is very similar to what we were used to doing with a string format, but this was deemed to be too verbose, because it's true we needed to then have format, value, and that's the default. Sometimes you have to do the assignment of the variables to the particular in here, whereas this one seems a little bit more natural and it's definitely more concise. So you just put the actual name of the variable in here, and that allows you to have exactly the same behavior. So it's just a way of doing it more explicit, more succinctly than having a string format. So that was just an alternate string. If you want to read a little bit more, you can go to PEP 0498. Those also part of what we saw last time. We already talked about the store attribute that allows you to assign the parameters for the class just in one line instead of doing it. So again, we have many ways of doing things. We're just seeing these particular like optimizations on how you write the code. It just makes it more efficient to write code this way. If you have a function that allows you to make 10 assignments instead of 10 lines of assignments. Let's see. We talk about the object list, which is a collection that from past code that they created. And this shows how you can do things that you could not have done with a normal list, Python list, like do this kind of assignment in here. And this category map, we're getting to a part, I believe. This category, and we're getting to a section that we left the last time. What was interesting here, not only that we use the list in here, but that the values, the functions that then we go and use in here, val to index, comes from that, right? Because items is a type of list. You can see that this function that returns the mapping between the values and the index was part of actually of the list. What else? Oh, we saw that how to detect non-NaN objects with if the object equal to equal. So if our object is equal to itself, then it's non-NaN. If the object is a NaN, then it will not comply to being equal to itself. The last part, how we use default dictionary, and that allows us to put the NaN, because the NaN, when it has no value, will by default int, because we put it as int in here, will default to 0, and that will allow us to have the index of the NaN to be that, and the index of the other elements to be the values. Then we just saw some example of how it works, how we can have, it's going to be order categories, usually they are ordered, and how they can be strict or not. A strict would just mean eliminate anything that you didn't actually see in the data. In the class category itself, this is the transform. So it does, of course, it uses the category map that we're doing, just that we were saying. But what was interesting is, so imagine that you get this transform and you got the labels, right? The input is usually going to be the labels, let's say dogs and cats. And then the first thing it needs to do is create the vocabulary if it doesn't have. You can put the vocabulary, but if it doesn't have the vocabulary, the setup goes and develops it. So goes and looks at all the possible values of the Y and develops the vocabulary, and tells you also the length of the vocabulary that you can use later. And what else did we say in here? It was interesting.
So question around the vocabulary. So when you're talking about dogs and cats and so on, when you say vocabulary, what are you referring to there?
So that has to do with the encoding and the decoding, right? Imagine that you have the images of the pets, and the actual class is whether or not it's a cat, right? So the vocabulary could be cat, and then, but for the actual operations, you need to have it in tensors. So you're going to encode it, and you usually encode it by using just indexes. So you're just going to use 0 or 1. You're not going to use words. Imagine that you're doing some classification where you have the class is going to be dog or cat, but the way that you're going to be transforming it or using it in the actual calculation is going to be just the index. So it could be index 0 or 1. So when you're looking at your values, let's say at the values that you have on the batches and all of that, you're going to see the 0 and the 1. The encode is the method that gives you the tensors, what you're going to use in the GPU calculations. And the decode is, okay, but how do I interpret? When I say 0, what does 0 mean to me? So that decoding is what allows me to interpret that the 0 could have mean the cat or the dog or whatever was the value. And in our case of the MNIST digits, encoding could be 0 or 1, and the decoding would be the value 3 or 7, which is the actual class. So the vocabulary will be, in this case, the string 3 and the string 7, because our classification is trying to determine whether a image is a 3 or a 7.
Oh, so it's the different classes. That's
correct. The different classes in a readable human format, let's say. Something that when I print, let's see if I have something, I think I have it at the end, when we have the here. You see how this here, we have a 7. That's the decode value, right? That's what the vocabulary tells me. And this 7, it might be mapped to an index. It could be, in this case, we only have 2 classes, so it will be mapped to an index 0 or 1, which is what we use in the operation. But then we decode it to be able to interpret it and understand this 7. So yes, vocabulary, sorry, it just means the classes. In this case, 3 or 7 could be dog or cats, whatever that our problem is.
And in a multi-class situation, it's just a set of classes that you have in your labels. And you'll see that very quickly when she just goes over the tests, then you can understand what the vocabulary is. But it is, in case, just as she explained it, but and in multi-classes, it's just a set of labels that you have.
Yeah, because in a multi-class, like the planet or satellite images, in an image you can have, I don't remember the classes, but let's say clouds and a river. So it could actually have to say that both classes, right? So that's the vocabulary would be, it would have river as a value, and then the other one too. So it will be active. It will have each image will have a list of classes. Whereas in this case,
okay.
we only have one value.
Yeah.
We're gonna get to categories in a second.
Okay. So, so I mean, in most of these, you know, if you read around the subject, it's often called class names and so on. Is that term taken somewhere else? Why they've used vocabulary rather than class names, which seems an easy one to understand?
Are you just saying why is the terminology used vocab?
Yeah, it just seems a bit odd given that we've done this a fair bit before, okay, so it's a big, so NLP, vocabulary is NLP terminology. So are we saying that it's because we're going to be using the same sort of thing for NLP or images or tabular data, and so
yeah, I guess that's what Jeremy is trying to do. Yeah.
That's a good point.
just trying to understand that.
Why use the terminology vocab? But yeah, you're right.
Okay.
So notice how, so there's here we're decoding. For example, in this case, his test. So let's start at the beginning, right? We're saying that we're going to have a transformation that is going to be categorized. Our data set contains the values. Remember, each one of these is one item. This will be the Ys that correspond from the images in a real problem, for example. So it will be cat, dog, and cat. This is just enumeration. If you have 20 elements, obviously a lot of them going to be repeated. And we're saying that to this particular data set, we're going to apply the transformation categorize. Once we apply the transformation categorize, we can see that the vocabulary is going to be cat and dog, which is the unique classes. I hear you. So vocab is like, what is the list of unique classes in this case? It's just, it's category, not multi-category. And then we can see, furthermore, that it's doing this transformation, encoding and decoding between the indexes. We can see that decoding the value 1 will be a dog, a cat, and we just put the actual class. Then it gives us doing the encoding. So if we encode the class cat, it's a little confusing because cat is short for category, and here we're using a cat, so ignore that part. But the encoding that corresponds to the class cat will be a value of 0. The encoding that corresponds to the class dog will be a value of 1. So in this test equalities, that's what is making sure, because we only have cat and dog. And notice that we know that cat has to be value 0 and dog has to be number 1, because by default, we're saying that the labels or the classes have to be sorted. So alphabetical order. So we know that yes, cat has to be 0 and dog has to be 1. Okay.
Also, just like NLP, he creates the reverse dictionary, and that's what the O2I is. So you can go back and forth. And that's exactly as Rachel pointed out, and you were saying it's NLP related because we use in NLP the reverse directory as well. So. And
remember, we're using a list here. So let me see. O2I, that's the other one I wanted to see. This is object to index, right? So from the items, we can see what is all the possible classes, but object to index give us that mapping between what corresponds to dog, what corresponds to cat. Remember, the 0s and 1 is what we're going to use in our operations. The dogs and cats is what we're going to use in your actual methods show. So always think, when I'm going to see a batch, let's say that way, when I'm going to try to interpret, the decoding is what it tells me what is the label that if it was an image, what is the label that I'm going to put for that image in this particular case. Let's see. Okay. So what else we saw here in this case, the difference between these categories and these categories is that we allowed NAs. So the vocabulary in here, as you can see, allows for the NAs, whereas in here we didn't. That's the only part. In here we didn't sort, which I find not really good. I like sorted because I know exactly what is going to be. In this case, since we didn't sort and it's in the order that the items were received, cat became index number 2. I like to know that cat will always be index number 0, so I like things to be sorted. But if you have a particular program that likes to have it this way, that's fine. I think that's how we left it last time. So we can start from here. So multi-categorize is just an extra form. Notice how we also assign the last function. So this is the part when it becomes smart, right? That it knows that without me having to apply the long function, but it's because I did tell him what kind of Y I have. If I know what is my target, then I can know what kind of loss I'm going to use, and it's just doing it for you automatically. So this is how it does it. It just assigns what is my loss function. We saw the order, it's still order 1, because we're gonna usually get the label and then encode it into tensors, which is what we do with these multi-categories. So also I just want to mention that yes, we are, when we encode, again, we're trying to get tensors. Even when we're doing images, when at the end, we want to have tensors. So this is what we're doing in this case, directly encoded into a tensor. And when we decode it into a multi-category. That's another object that we have. This object, multi-category, should have a method called show, because again, that's what we're decoding. We're decoding to be able to show you on a screen how it looks like. So the output of encode is tensors. The output of decode is an object that has a method show. Let me see if there's anything else. In here, well, the other part of multi-category is that, as we said, every item now is going to have a list of labels. That's the difference before. Before, it was one particular class, unique class. Now every object contains a list. Also, for the same reason that we have a list, when we're going to think of that method show, it's going to have to show what is all the elements in that list. That's why it has to define its own method showing here. So it cannot just be used the method that we were using for category, because in category we were just printing one value, and in here we need to print a list of values. So we can see here, that's why we use this part here to just join all the possible. For example, if these images contain rivers and clouds, so it's just showing rivers, comma, clouds in here. What else in here? We can see the values in this. Again, we only have the targets in this particular data set, but the target is that this image contains the class B and C, the class A, the class A and C. So if we look at this, the book here is the vocab. The vocab is again just the unique classes. So the unique classes is A, B, C. This item has 2 classes, but the unique classes would just be all the possible unique classes, right? We can make sure that when we decode, again, because it's alphabetical, the index is going to correspond of the object B is going to be 1, and we can test the code with a list. So that way, if I'm trying to decode what one particular image had, and the image had these 2 classes, then it's going to decode to the normal. So this is just to show the functionality of encoding and decoding now works in this object that is a list, a collection. One hot encode will just create it.
Sorry.
Yeah.
Just have a question there with 88. So on the cell number 88, we created the line number 2 TDS, which was just the data set. What exactly are we testing on the first test? TDS of 3.0, you're basically testing the type to be multi-category return, right?
Yeah. It sounds like.
Yeah, so 3.0 is empty, right?
Oh, it's actually saying that it's an empty value. You're right.
Oh, you're saying, okay. But
yeah,
how is that
value.
getting, what is getting encoded over there, like in terms of vocab? Is there something special with the vocab going on there, or is it just not considering it's just empty?
So the vocab itself won't change. The vocab, imagine that the vocab is just the enumeration of the unique classes. So this particular item that contains no classes doesn't add anything to the vocab. So that's different, right? It doesn't add anything. It doesn't add a new item that says no class.
Okay.
It does not add that. But in this case, what you're saying is that it can have an empty. So that's interesting to note, that we can have an empty list of classes. So one item can have a target nothing, because that image just didn't have rivers or clouds.
All right. So that's why I was wondering, if you have a class like that, I mean, so let's say there's an image which basically maps to nothing, right?
Yeah.
So like, how does that help in terms of building your code? Like, that's why I was just kind of confused over there.
No, it does help you, right? You're still mapping it to empty. You don't lose. This is image 0, image 1, image 2. This is image 3. you're saying image3 is going to be mapped to empty.
Correct.
It doesn't change the vocab. A different way, this is not doing that. And there are other models. If you're building your own very custom model, maybe you want to create a new class that means no object, but that's a completely different design method than what we're looking at here. The text transforming, for example, the new object detection from Facebook, that's that. That's that because it wants to always detect 100 objects. The image might only have 3. So 97 of these detections for image are going to be empty objects. But that's a very particular design of the model that is not what we're doing over here. So in this case, yes, it's an empty, but you're right. Thank you for pointing out that in this case, we're just checking that this particular item or image, let's say, the target of that image that's represented contains no classes. It doesn't affect the vocab, but it's empty on the classes. Let's see what else. In this particular set, we just said that it's going to be, notice how we can say tensor and tensor category, and we're gonna go into type dispatch. I don't wanna talk about it here, but we're gonna get into type dispatch on the next notebook, but let's just notice how we have tensors and tensor categories over here. Another thing that is interesting is this test standard out is part of the testing. So we saw that test equals is one of the most common one. But test stand out, and I think I have it here. Yep. It actually checks something that it was going to print. So it compares that what the output of the print method should be, and then make sure that it's exactly what you expect. So I found that really interesting how you can actually test the output of a print method. Oh, I went to the next one. Okay. Okay.
Sorry, the one other thing which is really interesting in that particular cell is the fact that every element of the data set is actually a tuple. So if you try, for example, to print TDS2, TDS at index 2, you'll get back. So if you do print TDS2, then you'll get back a single entry tuple. And its type is actually a tuple. And if you try, for example, to print TDS2 index 0, that's the single entry value of the TDS2 tuple. And then if you want to get the first value, that's 0, yeah, you won't find 1 because then you do TDS2 0 and then one more index into 0 and you'll get the actual 0 inside tensor category.
I missed that part. So I see that
that's item.
Sorry?
That should be dot item, I think. Dot item to get the actual. I think was a method.
Call.
Sorry, why is this a tuple?
The data sets always contain tuples of items. And so that's what I found interesting, that each element is actually a tuple.
Yeah, it contains
it's usually a tuple because it contains the
images
X and the Y.
Yeah, the X, the Y, and in this case we only have the Y's, right?
Correct. Yes.
Yeah.
Yeah, it is meant to, and we're gonna get to that part on the type special. So that is meant to always have an X and a Y. It's just confusing here because it's not real, so we don't have our X. I don't have much here on the one hot encode. I didn't look at this in detail, except that again, encode is a tensor multi-category, and in decoding one hot encode. We're gonna see if we wanna look at it this way in here. Which assuming is gonna give you that's a very interesting. I'm not certain what it gives you, so let's look at it. One hot encode of, we have three classes. Yep. And I want to hot encode 0 and 2. Okay, so I'm going to get 1, 0, and 1. And if I decode it, it's going to be telling me that I have, in this class, this is class class 0 is not present, class 1 is present, class 2 is present. So if I have to decode that, that's going to be 1 and 2. Okay. Just what would be the one hot encode of that? So that would be the same as this one in here. I guess if that's what you want to do with that one hot encode, I haven't used it as a transform, but okay. So you can first multi-categorize and then one hot encode. Why would we need to multi-categorize first?
If you're doing multi-class classification.
Oh, yeah, you're right, because we receive, multi-categorize receive the list of classes and then convert it, encode them into the list, right? Is the one that is giving you the list. What are the classes that is representing, but it's, again, is represented at 0 and 2, whereas the one hot encoding of this would have been 1, 0, 1, for example, for this tensor 2. Okay.
Yeah, I think the major reason why that's done is because of we're using binary cross entropy. And you know, binary cross entropy is zeros and ones. So you don't want your labels as your classes to be like, in our case, is 0 to 3. 1 to 1 hot encode everything to fall between 0 and 1. Yeah.
Got it. You need to have it for your loss. Okay. I didn't have anything on regression setup, transform, or encode multi-categorize. If anybody has any interesting comments on these ones, please let me know.
Just to clarify with Tendo, does he mean that the multi-categorized experiments that we have in the notebook is one hot encoding inherently added with that?
This is not one hot encoding, right? This part in here is doing both. Let's, if you want, let's do it by part, right? In this here, we have our data set, okay? So our classes, if we look at our vocab again is going to be classes A, B, and C. Let's say A, B, and C are type of rivers and clouds in a satellite image. So your classes are going to be A, B, and C. You first multi-categorize, and then you're gonna one hot encode. The first thing that you're going to do with multi-categorize, you're gonna do the mapping between A, B, and C to the indexes, right? So you're gonna map the class to the index. So we say that our vocabulary is going to be A, B, and C, which means A maps to 0 and C maps to the number 2. So first transform does C equals 2. So now you have, if an image has only C, you have that map to a number 2. Now you can go in and then one hot encode that number 2 that you have 0, 0, 1, for example.
But so that's what, so multi-categorize itself, by itself, the transform is enough for doing like planets, right? You're saying, right?
Yeah, yeah.
Okay.
But sorry, I missed the person who was explaining us that depending on the loss function that you're going to use, you might be expecting it in one hot encode.
Yeah, multi-category problems in general, you use binary cross entropy because you have multiple windows for each class. Yeah, and in order to use binary cross entropy, you have to hot encode.
Yeah.
But that's what, so multi-category by itself is taking care of the binary cross entropy. You don't have to one hot encode from what I remember to do binary cross entropy is what I'm thinking.
Remember, multi-categorize is giving us this output, right?
Yes.
So the difference between getting that. So that was, imagine that was, we start with dog. No, well, in this case, we're saying C. We start with that. That was our class was C. Multi-categorize will get us, oh, well, that's our index too. And then the binary gets us to 0.
Yeah, I think I understand your query. If you're using the data block API and you call
exactly.
If you call multi-category, one hot encode is done in the background.
Right.
If you should construct a multi-category problem with the mid-level, the data sets and the data loaders on a normal, you have to pass in one hot encode. But since you're using the data block API, it's done in the background for us.
Okay.
And then we can then encode it here. I believe that does it in the 2 steps. Yeah. Transform one hot encode the category that it goes with vocab. So
this is like a mixture. Yeah.
A wrapper. Yeah, that's both of them. As we can see, we were using the same.
So that's what. So in the data block API, this one specifically is encoded multi-category, right? It's not multi-category. That's what I'm trying to clarify.
In the data block API, you can use multi-categorize.
And
Then
that
in
will
the,
still use binary cross entropy under the hood, and you don't
yes,
have to one-hot encode, right?
yes.
Okay,
Yes.
okay.
It's just the same as normalize. If you notice, most times you don't always specify normalize when we're using the data block API. You can specify, but in the background, it's still done.
Okay.
Something that automatically. But if you are to build from scratch, then you have to specify all these little details.
Okay.
Regression seems really straightforward. We just have the encode and the decode. Encoding again, we just want to make sure that we have tensors, in this case float tensors. In the decoding, we have this title float that again, all we're doing is making sure that it's gonna have a show method that is going to pretty print floats.
Yeah, I have to point some. This regression setup is pretty important because it's actually run into a problem once now. So, okay. It doesn't apply when you're working with the data block API, but it's very important when you're working with the mid-level API, the data sets. Because if you're working with a regression problem, you can't use categorize on the labels. You have to call regression setup. It took me a while to figure this out. Actually call regression setup.
Let's just go to the example, and then unless you have any questions about after item and after batch, I think that these three were three functions. I think we're gonna see them in the next notebook, but I remember that it was after item, before batch, and after batch. So this is operations that you're going to do at that particular, when you're trying to, on the data loader, you already have a transform data loader, TFM DSDL, and then what operations you're gonna do at the item level for each one of the items in your batch, or you are doing something that you do when you're preparing your batch or after you do the batch. For example, you may want to show some metrics after you do some batch. I'm not certain what this one does. So, if anybody has any insight on this one?
Yeah, basically those three are the key callbacks after you create an item, after you have batched the items, and the before batch is actually after you have created the items, but before you have created the batch. And those three, if you will, times points in what you do, what you end up doing, you'll see, as you said rightly, in the data loader and data loaders, especially the data loader code and the transform TFMDDL transform data loader code, why you need those 3 points to be different, because there are some specific functions and or actions you need to take once you have created the item. And once you have created the item and before you have collated them into a batch, you need to take some steps, and after you have created the batch, you need to take some steps. So those three are callbacks, and those callbacks will do different things at those times. And we'll see that in much more detail as we get into the next several notebooks.
Okay, so in here we just want to put.
Sorry, I won't call them callbacks, but say they are transforms.
They get used in multiple ways. So you will see that they are used as callbacks in the.
We'll check.
Yeah, they point to the training loop where there are different callbacks, basically, right?
Yeah.
I think we're going to get a little bit on the next notebook, and if not, we can review after. So just here to put things together, remember all we have seen is I start from my data set, which was just the directory with all my images. And then what do I have to do? I need to go and get all the files. I need to then split them into train and validation. And then I need to be able to label. So we're just processing my target. What am I going to do with that? And so we have with categories and multi-categories and all of that. So let's put it all together in one example. We just get the files, the image file from this particular path. We know how that functions. We define a splitter that is going to be grandparent splitter. That just means from the path in here, I'm going to get the grandparent, which would be train or valid. That's just the directory or the folder. That's like what the grandparent splitter. So I'm going to split my data set because it's already a structure and it already tells me which images are trained and which images are for validation. And then in here, it's just, now we're going to put our transforms here. It's a list of transforms, and then we're going to apply. So notice how the data set has two elements. What is the actual data? and what is the transforms that I'm going to apply. The actual data was in here. We generated with the split, so that's the data that we're gonna use. And then we have this pipeline of transform, and this is when in this particular pipeline is when we start having these tuples, right? The first element of the tuple is that transforms that I'm going to apply to my X, and then the list of transforms that I'm going to apply to my Y. In this particular case, because he's just writing code to testing here, we're not using transform per se, we're using functions, but the functions get converted into transforms when I'm using them in this way of the pipelines. Categorize was a real transform. So when we have a real transform, we have all the parameters specified to not default values like the order. So we can see here that categorize has order 1. This particular function, because it was not a transform, by default we have order 0. So in this case, they're gonna get executed first this one and then categorize. Even if I put categorize to the left of parent label, because there is an implicit order, well, there is a value that tells me in which order I should execute the transform categorize, it will respect it. Whereas in the first case, because both of them are functions, both of them default to 0, so it is important that I put them in the right order. But in reality, we don't want to be doing this and putting functions. We want to put transform. This is just because it's an example. But the code that we want to be writing should be having a list of transforms such that they already have the order specified.
Yeah, so sorry to give you the key is anytime you specify that kind of a list of transforms, it's essentially a pipeline, and every element of the pipeline, whether it's a function or a transform, gets transformed to a transform, or gets converted to a transform whenever you provide it. That's why even a function, if it isn't a transform, is converted to a transform. If it is already a transform, then it's obviously a transform. But that's a pipeline, and we'll look at pipelines in much greater detail in one of the upcoming walkthroughs. But that's what you're pointing out.
I have a question. It's pretty stupid. Well, is there any way to specify the order which these functions should be?
Yeah. So categorize, when we were doing categorize.
Yeah, I know about normal transforms. But I mean, when you pass in functions, is there a way to specify the order? Like in our case now, we did open images first. In the
you want to do it this way, right? That is going to take the order on the pipeline left to right. If you do it the other way,
it will fail. It will fail. Yeah, but I'm last. Is there any way to make it not to fail when it's that way?
I think if you just inherit from transforms, which will be converting it to a transform, that function, and then you can do a dot order on that. That's the only way I think. I know.
Yeah. Sorry. Yes, I meant to say categorize it's a subclass of transform.
Okay, so maybe you could call a decorator, transform decorator.
Exactly. Just have it it's as easy as putting just the decorator and then doing dot order on that if you want to specify the.
Okay, that makes sense.
In this case, because we don't have forms and it's not protected by the order, we cannot change it because then it's not going to be able to work. But now it works. Well, so we saw that in this case, yes, left to right, and if not, just two classes for transform and make sure you put the order. So all we did from here is take the third element. If we go and lead, we can see with just one particular image. And we're gonna decode So we decode it and then make sure that, we decode it with the method parent label. So the parent label, if we apply it directly to the same value, it should give you the same as the Y because the decode should be applying the parent label. So this is just making sure that the encoding and the decoding are working. I believe. At the top, and because we decode it, we can say that we can always show it. That's why we always do the decode, to be able to show. The X is an image, the Y is just a category, so the category will just be a label over here.
So one more thing I wanted to point out. Sorry, go ahead. Who was talking?
No, I just wanted to say show at internally calls decode.
Yeah, and before that, the thing I wanted to point out was parent label. If it's a function and a function doesn't, a function, remember, uh, gets converted to a transform, as I said, in a pipeline, and a transform essentially is nothing but when you call it, it calls the encode, which is essentially its call function. Now, in a function, there is no decode, or at least there's nothing to go back. And therefore, when nothing is specified on a decode and it becomes a transform, then you just spit out whatever is given into you. So a function, when used in a pipeline, and when it's used as part of decode, it just returns whatever it's given. So it doesn't do anything with it. That's important in
I think to generalize that encode and decode, if nothing is specified, you just basically get whatever is, like you said, taken in is just spat out directly.
Right. But no, when an encode, the function is applied.
Right. I mean, in this case, I'm saying when an encode is not mentioned, like in a transform.
When an encode is not mentioned, then nothing. But but otherwise, the function is applied when you're going forward as an encode. But when you come back, there is no decode, and so whatever goes in comes out.
Right.
Yeah, thank you. That's a good point. What are we didn't cover it?
Is this similar to this NUP? No operation.
Sorry,
yes, something like a NUP.
Yes.
Yeah. No.
Yes.
Yep.
We know that we always want to have tensors at the end during our processing. So the order usually tends to be 5. So just if you're trying to say it's going to be the last stop, first we're going to open the image, we're going to convert it to image tensor, and at the end we're going to convert it to tensor so that we can do operations. So, I believe that's what we wanted to say here. The other part.
Sorry, I think going back, I think Rachel, maybe you want to expand on what you just said, because I think that's an important concept as well, that actually show at calls decode underneath, and decode goes in the reverse order to give you what you want.
Right, yeah, I just wanted to mention that, and then I think when we move ahead, you'll see that decode actually uses what your activation is and like what your vocab is to kind of take you back. But yeah, you don't have to decode beforehand to do a show. The show does that for you, or the show at, yeah.
And I guess we're going to get to the part of when you are encoding, what encode method you should use in a transform, right? That's the part that you're going to do it based on what is the type that you receive. And we're going to get that in the. So if what you receive is a tensor image, then you're going to return this method. You're going to execute this part. If it's a tensor mark, you execute this. So this is just the type dispatch based on the particular type. I'm just going to skip it because we're going to see it in detail on the next notebook. Normalize looks familiar to what we were looking before. You just need to make sure you set it up, because if you don't have, you need to have sense of the statistical values of the mean and the standard. If you don't have it, well, then go and read one batch, and you're going to be able to have a values for mean or standard deviation. If you already have them, then you don't need to generate them. You need to go read a batch and have some proxy values, and then you're just encoding it the normal way, applying the normalization to that one. So the only interesting in here is I want to normalize. I don't have any values. Don't worry, setup is going to take care of it. It's going to go read one batch, and it's going to create the values that it needs. I don't know if this is meant that which operations are being done on the GPU because they're inside the batch. I don't know if anybody has any. I see that we have the broadcast in here, and we're executing it on
default device will be set to CPU or GPU based on what you have. So if you have a GPU, it'll run on the GPU, or else it'll run on the CPU.
In this case, my runtime is CPU, so let's not ask because it's going to say CPU, but if you have a GPU, then it will.
Right, yeah. I think you can kind of see that I think the default device before initially set to like whatever device you have that is available. The important thing with normalize is you want to use, traditionally you want to use whatever stats your model was built with, like if you're using pre-trained weights. There is another instance here, if you look at the setups is the case where you're passing in data which does not have, you have not specified your stats. What FastAI does by default is it grabs only one batch. So even if you pass it like 10,000 images, if your batch is like 64, it's going to just grab one batch and it's going to create your stats only from those 64 images. So that is something.
That can have some undesired effects, you're saying?
Sorry?
That can have some undesirable or lateral effects that it might not be very representative. You're
Exactly. If that one batch is representative again of your whole data set, then it makes sense, or else no. So, I mean, the easiest thing is to just calculate your stats by yourself and pass it in. The reason why FastAI doesn't do that, what I suspect is it takes a while to compute that every time, right? So it's such a waste of time every time you run this thing that normalize has to be computed. But in reality, you just need to do it once. And once you've computed those stats, you can always pass those in.
Yeah, I read somewhere Jeremy and Sylvia, they made a study like that. They were like, if your batch is big enough, that if you should collect just one batch, like maybe up to 64 or 32, that it's maybe.
Right. Yeah, in the book they mentioned that like if the batch is representative of your data set, then obviously it makes sense to take that mean. But let us say if a bunch of classes is not even there in that 64 set, then you start getting into like little hairy areas. It's just something to keep in mind here.
Yeah, I agree.
Yeah, but that's also, I mean, I think the point you bring up is the classic FastAI and why, in a sense, we are diving into the details. So the library is very oriented to getting you up and running very quickly using defaults, so you need not be aware of all these details. However, as folks who want to get into the details, we need to be aware of these because now, that said, the library also provides you the ability to do whatever you want. So it's also very flexible, but you won't know where you need to make those changes unless you dive into what the notebooks as we are doing currently. So the point being
that's true. That's a very good point, right? All of this is to let you start from nothing. Remember from the beginning when we ran our first notebook, it was a notebook that had like 5 lines and that's everything. Because there is a lot that is going under the hood that is making like this, assigning what is going to be the loss function, doing this part of like, don't worry about doing mean and standard deviation, I'm gonna take care of that for you. So it's true. It takes care of a lot of things in default methods and values for you so you can get up and running in 5 lines. But then if you want to go more advanced, go and modify.
Exactly.
Agreed. I don't have much, so unless you have something from here, I would say let's go to the next one to get to the type dispatch, which was, I got this part to work, so that was good.
If you just go back up to, I wanted to just say, just one more, I believe, somewhere up there, sorry, in the, in normalized class itself at the bottom, the F function is what you're referring to earlier too, right? It just moves it to the CPU, and if you do, otherwise it does nothing. And that's also related to what you eventually want it to run on, meaning the CPU, or if you have the device set up to be, or if you're already running on the GPU, then it'll run it on that.
Isn't this more?
Why would this happen? So why would be?
So my understanding of that line is that whenever you're trying to do these displays, probably this is when you're checking your stuff, right? At the end of the day, is always you want to pull it back to your CPU, right? And
exactly.
This is inherently taking care of it because it's much more messy to deal with the GPU.
Right. Not in the general case, but in the decodes case.
Exactly.
Because you want to display it and.
Another thing worth pointing out is in the setups, you know, when he calculated the standard deviation, he added like an epsilon, 1 in X7. I don't know if you guys can see it.
Right.
Yeah, so it's like, I forgotten the word that they use for that.
Divide. Otherwise, you divide by 0, basically. So let's say if your standard deviation is 0, it would explode things. Yeah.
Yes,
It's
yes,
like
yes.
he often uses
Epsilon. Basically.
EPS,
Epsilon.
but in this case, he just directly slammed it in, which is very unlike him.
Yeah.
Yeah, that's true. Okay. Yeah, so we are halfway, so let's just go quickly to this part. So the other part that we covered on the walkthrough number 2 was this new notebook data core. And there were just some points that were interesting. I believe that 2 things were the most interesting, which was the type dispatch. And then there was something about delegates and the keyword argument. So let's just make sure that we cover those. So the first thing was that we're talking about transform data loaders. So before we're talking about data sets. For data set, we have 2 components. The actual data, usually it's going to be just the train part of the data, and the list of transforms that we're going to execute on that data. Now, we need to think about, once I want to generate a batch for the actual algorithm or for the actual optimization, then I need to create a data loader. So the difference between data set and data loaders was, now I'm thinking on batches. So when I'm let me see. Oh, in this case, he mentioned that when we're trying to show a batch, clearly, what you're going to be doing in that method depends, what am I talking about? If my batch in X is going to be images, then my method show batch is going to show my 12 or whatever the size of my batch is of images. It's going to make a display of 12 plots, or it could be something that it could be tabular data, or it could be NLP. Therefore, it needs to know, what am I talking about? What is my object of the type, to make sure that then I go and apply the correct show method, show batch. And it has to do, I believe that's that part here, with this part that it calls type dispatch. So a good explanation. This I got from Jeremy's blog post in here. So he has this from February, and he explains it over here on the type dispatch, but basically it says that it was similar to this example that is already provided in Python. And I found that one to be really easy to understand. So imagine that you just have a function add, and you define it, you define a method, and to define the method, you register each of the possible types. So I register an add a method for ints, and I'm gonna say a plus b, and I'm gonna make sure, in this example, I'm gonna say, well, a was an int, so I register for int, I register for a string, I can have an add function for a string, and I register for a list. So I have so far registered for int, a string, and list. If I called my add function with something that is not an int, a string, or a list, then I'm gonna go and default to single dispatch, which in this case I say, well, I'm not implemented because I haven't created anything like that. And then we can see that you can execute it with your integers, your strings, and your list. And you're gonna be able to get the values, I mean, the execution, the addition of integers, strings, or lists. And if you give it something that it wasn't, in this case, they say if you give it a directory, then it's gonna fail. And it's gonna say unsupported type. So I believe that's kind of what you're going for here. Notice how in this case, then you have to keep a register to know, well, what are the methods for which I have implemented? So I need to have a registry that tells me, well, you have it for ints, for strings, and for lists. So as long as it comes from any of these methods, well, if it comes from int, you're gonna execute this method. If it comes from a string, you're gonna execute that method, and so on. So I think that was what is really important in here, particularly in this kind of functions, show batch and show results. Let me see what else was there. Something that is really interesting is in particularly for us, for this library, FastAI, we're talking about this multiple dispatch over 2 parameters, because as we mentioned, we usually have a tuple. We have our X and we have our Y. So we want to have a bunch of our dispatch methods has to do with what is the type of X and what is the type of Y. And this is the example that he put in there. You can have a generic method based on a generic value for when you're just specifying for X, and then you say nothing for Y. So if it doesn't match any of the other ones. It doesn't matter what y is, I'm going to execute this particular function. Or I can have, well, in particular, if x is an integer and y is a float, I'm going to execute this method. So this has to do with the matching of what is the particular method I should execute. For that, we wanna
Sorry. So should both the parameters match or just the first one?
In this case, well, you can do it both ways, right? In this case, both of them need to match because I'm specifying. In this case, if I don't want to worry because it doesn't matter what y is, I just don't specify it, and in this case, only this one needs to match.
Okay.
So I can have it this way or not. In reality, if you want to see how he implemented, let me see something that is interesting in here. Yeah, this is the example that I was showing in here, the global registry that tells you which one you should execute in here. And it does, so something that was interesting, I don't understand very well, but the part that it does the casting, and we're gonna go back to that part of going back to the casting and how it retains the type. We're gonna go that in a second, it's gonna be after.
Yeah, he goes into much more detail in type dispatch in subsequent walkthroughs. So if we don't get it, then I think.
Okay, I just mentioned this part of because this was interesting on the transform themselves. So remember how we're saying that we had a tensor-based class, right? And then we have classes that were on subcategories, subclasses of that, like category and multi-category. So they were just subclassing this tensor-base. Like tensor image was also a subclass. So they do it because they want to have this control where they can instantiate in subclass. And then
and as we go through the rest, there is a reason why that he wants to put that back, and we'll get into it just later in this notebook or in the very next notebook. There's the end.
Let me see if
for the explanation till then.
Yeah, I think we're going to get in a little bit of detail in there, but basically what we're going to do is we're going to make sure that there are some operations that when we execute them in PyTorch, we lose the class that we were referring. Remind me, we have a tensor image. We execute some operations, so we somehow went back to tensor. And we want to make sure that the transform knows that to return it or to instantiate it back to a tensor image. So this part of retain type is this mechanism is gonna take care of it because it's gonna say, if my new class is tensor, but I was originally a tensor image, and this tensor is a super class of tensor image, I'm gonna make sure that I'm going to then instantiate it. So I force it back and convert it back to tensor image. We're gonna see, I believe, an example in here. So let's just go there. So far, we saw the type dispatch. I really like this example that he mentioned over there. And he said that both for show batch and for show results. So for show batch, X and Y are the input and the target. Yeah, so because the X, as we mentioned, can be a tensor image or a tensor text. So how should I be displaying? Should I do a print or should I do a plot? And then that's how it knows what particular function it should execute because it belongs to the particular class. And then the context, I believe the context are like the Jupyter notebook or like the particular plot that we're working on, I believe. I wasn't sure. Up. Let's see. Oh, and here we have this. It's true. There's called them batch transform. The thing that we're saying whether it were callbacks or not, after item, before batch, and after batch.
They are callbacks as we discussed in the chat. It's just that they could be attributes or they could be, as Fendo was pointing out, other things, but eventually they turn out to be callbacks.
Oh, did I lose PMFL? I hope not. Maybe my notebook was not executing program. Just make sure I have PMFL. Okay. So the other part, hopefully it will work. Nope. Oh, because I have it here. It says clearly execute this after. So it's not that perfect. Okay. So the other part that we want to see is that in here. So let's look at our class transform data loader, right? This has a lot of points. So let's just go to my notes. Well, we want to delegates and the keyword arguments. Oh, okay. So for this one, it's important to see that we have some parameters that we want to specify on the init method. And then at the same time, it's going to inherit a bunch of other ones. And that's what we're seeing here in the show doc. Because this one is a subclass of data loader. In here, I'm just 1, 2, 3, 4, 5, 6. I'm specifying 6 parameters, but then I send in anything else on my keyword arguments, right? So those keyword arguments is going to take from the superclass data loader. So I can specify device, before item, create item, all these other methods. And this keyword argument is part of Python. And that's normal what they're doing in here, such that we're able to use this part. And it says this nice example in here of why it's useful. So if we have a product page that is a subclass of web page, and I only want to specify the title of the price, I want to make sure that I'm able to specify the category and author, for example, that were part of the web page. So this allows me, these keyword arguments allows me to specify them without having to then rewrite in here all the possibles, right? And it assigns them correctly to where it goes. And key argument just means put any additional keyword arguments into a dictionary. So in reality, it's going to be a dictionary. That's why they have to be keywords. So I say which particular argument, and I say what is the value of it. Now that works really nice, and a lot of it, Matplotlib and a lot of other Python libraries make use of it. The problem that Jeremy saw on this particular point was, well, but when you use it in this case, for example, if I do a product page double question mark and I ask what are my values, or I try to autocomplete, it will only show me these 3. I don't have visibility. The rest of the keyword arguments get hidden, and autocomplete and show doc and all these other things of literal programming get lost. So then that's why he created this delegated inheritance of this delegate that in combination with the keyword argument allows it to take care of these parameters that were part of the superclass. And that's why we're going to be able to, for example, when we inspect the signature of the transform data loader, we're not going to see just the 6 parameters that we wrote on the init. We're going to be able, everything from the data loader will be visible here. And that will not be possible without him implementing this delegate. So this decorator delegates is what allows us to do that. Python itself doesn't have it. Python itself will allow us to assign the values, but we will not be able to see it on the signature of the function. So what else was there in here? So that was just for delegates, and that allows us to do these keyword arguments.
It also shows up in the tab completion.
Yes,
part,
and that allows for that tab completion. So that's what you get again, because the code itself, I was looking at it. You can look at it here again. It's interesting. I don't know if we're going to go into detail of how this is implemented.
Yeah, later on, towards the end, the last 2 lectures are devoted to all these things that he creates.
Yeah, good, because it sounded heavy. We just wanted to know right now that it exists, and this is what it's doing, and that's what all is on that part. And then we have here what we're saying that before iteration, and sorry, that was not the.
Yeah, actually, we will go through a lot of this actual code in the next lecture or walkthrough 3. So I think if we can go to the usage like he does, right? Yeah, starting from about there and cover the rest of the notebooks, that would be great, because he goes through the code of TXMD later.
On that. This was going back to this type part that we were saying. So we know that tensor image, again, is tensor image base. Tensor image base, we're going to go to tensor base, and tensor base goes to tensor. Let's just keep that. That's how it is, right? And we want to know this part that we said that we're going to be able to cast it to what it was. And the way that he shows that, that's what he's doing. He's showing that here because we have a negative transform. And we're using a touch function for that, which just does this negative in here. Now, when we encode it and we do torch neck here, we're going to see that if I just apply torch neck to, let's say, a tensor image, this, let's pretend this is my tensor image, and then I go and apply this function, what I'm going to get back is going to be a torch tensor. So I lost my tensor image part. It's a tensor, but it's not a tensor image anymore. When we do this transformation though, notice in here, he applies the negative transform and he keeps the tensor image. Here I printed it to make sure that we're still there. And that's what he's testing here, right? That even though we apply the transform, we took one batch, so let's go step by step. We're going to do my data loader in here, in which I have my data, which is just this tensor image. And I'm going to apply, this is my transformation. We're going to apply my negative transform. My batch is 4 and I have 4 workers. I take one batch. We can see that the type of the first element of the batch is a tensor image. We make sure that it was a tensor image. And then when we decode the batch, in here, he makes sure that he still keeps a tensor image, which if we didn't have this memory of retaining the type that I was showing you on the passport, where we keep track, what was my old class? And if I'm now a super class of that class, I'm gonna cast again, we will have gotten a torch tensor. So I believe that's what he wanted to show in this part of the transform. And that's what allows it, because if we lose the tensor image, then we, on the decode, then all our machinery to do the show, for example, will break because we won't have that on a torch tensor. So that's the part of, he built the machinery such that whenever we apply a transform, we're going to return to the class as long as it's a subclass of the superclass that we currently have, because sometimes we do lose it. I believe he explained that as, let me see if I wrote it here. Yeah, transfer automatically to maintain those classes. I don't think I have any other comments on that. Let me see.
Yeah, the reason why, as you correctly pointed out, is it helps you retain it so that, and this was something very early on, he was emphasizing that the infrastructure he has built is such that by the time you take it to actually applying the and using the data, everything is tensors, whether you start with images or start with natural language processing or start with tabular data, everything is tensors. So if that's the case, then you cannot use things like show at, and other stuff, because you don't know what they are, as you were just explaining. And what this enables you to do, what the transforms and pipelines that he has built, and the infrastructure of type dispatch and stuff that he has modified from Python helps you to do, is retain the types as as you went through in great detail, so that when you decode, you can utilize the knowledge that you came from an image and therefore show it as an image. The other thing that it's helpful for is if you're using in inference and stuff, then you know what data type it has, and that's something else later on that he'll also get into. The one final point I wanted to make is, as you rightly pointed out, tensor and pipelines helps you retain the types, or they put back the subclass type that went into the transform rather than what results from the transform. But the way to escape from that is to put a none on the output, and then you can escape from the default behavior.
Yeah, if you want to opt out of that behavior, then you do this part in here. So remember, in here we didn't have, right, the transform doesn't give us what is the return type. I noticed also there was one in here. Let's see. No, I don't have it, because sometimes you could see that it was specified very different types, and the encode function depends on which one type it is, but it doesn't specify this part of what was the return type. And if you don't want that to execute, yeah, because it has here none. So in this one, we have just this list of numbers, and all you're doing is transforming it to a tuple. So you didn't, I believe that you just didn't go back to it. Whereas in here, Let's see what was in here. Oh, here I have my notes. X was still a tensor and Y was the tuple because we have, okay. In here we have the same data. Star just that is the list of numbers that we said here was from 0 to 50. And then, but in here we apply this is a pipeline of transform, or you're saying that after you're gonna apply this tuple, you're gonna apply AX to the X's and FX to the Y's, where A was this transform that just encodes and returns title int. Title int, again, it was just to give us the show method, right? So we want to keep it that is a title int. And fx was just giving us the tuple, I believe. So when you have one batch and you look at the type of the y, it's going to be a tuple. When you decode the batch on xy, you're still saying that the y is still a tuple. I guess that's all I saw there. But I believe, yes, I agree with Fernanda. The point was if you want to opt out to the transformation that making it back, it's just this known to escape. There were just some more testing. They were testing just the standard out, which we already saw. Oh, I just have a question. If anybody knows what the unique parameter was in show batch, I couldn't figure out what this test was in here. So we have the same list of 50 numbers, and then we say that we're gonna test, this one is fine. We're gonna test that if I show the batch, my values are gonna be 0, 1, 3. That seems really straightforward because I just have the list, right? And we're saying I'm gonna get that batch. So if I do, for me transform order, I just wanna show my batch, I should get a list of 0, 1, 2, 3. If I run it. If I run all the ones I lost. Okay, maybe. Yep. There we go. Okay, so up to here, it was fine. Show the batch. I mean, we send the batch is going to 4 elements, so it makes sense that it's just 0, 1, 2, 3. The part that I didn't understand was what happens when I put unique? Why was it put 0? If I put unique equal true.
So unique is basically telling you to see all your possible transformations for just one image. So this is basically, show batch is going to be used initially when you're sending off your data to training, right? So when you're sending off your data to training, you perform all these transformations, rotation. When I'm talking of transformations, you know, augmentations, data augmentations that you're performing.
Yeah, in the image thing with the augmentations, I hear you because you can have 5 different augmentations. You flip it, you rotate it, you scale it. So you're saying that you just want to show the transformations that you did to one image?
Exactly. Unique is equal to true.
I understand that in the context of an image. I lost it on what it means in this case because I wasn't talking about images. It was just numbers.
So here you're not performing. Here you're not performing any data augmentation, right? So what happens when you do not have anything? The general standard is whatever comes in. If nothing is specified for me, just spit back what you got. So that's why it's unique is taking.
Then that means that if I have gotten exactly what I had before, I will understand it. But the fact that I lost what I have, so if I show my batch, I get 1, 2, 3, 0, 1, 2, 3. But if I say unique, I get 0. That's the part that, why don't you bring?
So you're picking just the first one, right?
Oh, I pick just the first element.
Right,
I don't know, I do 0 augmentations and I start for 4 elements in the batch. So
exactly.
it repeats. Oh, I got you now. Sorry. That makes sense. Thank you. I wasn't sure about that on the unique. And okay, I think that was it. Oh, and here I have another one that the transfer parameter is stored in the CPU. Oh, that was because we said that we define here a parameter And on the init, parameter A, and I noticed that it says that it's going to be on the device CPU in the after batch. But that's it. I believe that's not covered on video number 2. If we have anything else that will be on video number 3.
The only other thing I wanted to point out, sorry, if you stay right there, give me for a minute. The reason I said callback is also the tensor image, and then you get the tensor image 1 multiplied by 4, and after batch is when that transform is applied. So if, for example, you had specified this to be, I don't know whether it will make sense, but my point conceptually is if you specified this is before batch or after item, then when that transform gets applied is after it becomes an item or after it's batched. So in this case, you see, for example, that the transform B is applied after batch, which is why you say after batch equals. So all of the times, if you had a list of transforms that you want to apply after batch, then you provide that list on the right side of the equal sign.
And the pointing here with the touch device is that the batch was executed on the GPU, but the after batch operations are executed on the CPU. I'm trying to see this test equivalence here is saying that the device of the parameter A is going to be the CPU. It's not reading it. I mean, I can send my transform data loader to default, and if I was running a GPU, then that would be the GPU. But if I don't send it to the GPU, it's saying that it has to be on the CPU. That's the part that I was asking. I didn't see it on the video. We can clarify. Maybe I missed it.
No, it wasn't covered in the.
Yeah, I think that's when I stopped. When I started noticing things that they were not discussed on the video, it was like maybe it's covered on the next video. I just didn't get to watch that other one. But yeah, that's something that we definitely have to look. I was just intrigued by the CPU here of that part.
I think it's just saying that the default device is CPU, right? Until and unless.
No. Default device is here. In this case, because my runtime is on CPU, the default device will be CPU. I tested when I was on GPU, the default device was GPU. So if I send it and I'm on a GPU, it will send it to the GPU and default device would be GPU. But in here, it's not sending it. It's not doing anything. It's just saying, make sure that the device of the parameter A, it's on the CPU.
Yeah, that's what I'm saying.
Inference, right? It has to be an inference for it to be maybe.
No, in this case, it's just saying, as Rick saying, that it is and FSOA, I believe, is just the
like
attribute A of the function in FS or whatever. But it just says that I believe the default device, you don't move until you say TDL2 and then default device. And in this case, whatever your device is, it just is checking that it is still on the CPU.
Yeah. I believe once you make a transform data loader.
Sorry?
I believe once you make a CFMDL, the defaults, like the way it goes to on a normal is the CPU. So you now specify, if you want to move it to the GPU, you can now specify a 2 device, or maybe if you want to move it back to CPU, you can 2.
Okay. So when we put in here, because we didn't say anything, it's going to be on the CPU.
On the CPU, yeah. That's why the first test passed. Yeah.
Yeah. We can send it to the GPU in here, and then it makes sure that if we send it there, but if I
in this case,
right.
In this case, your default device is still CPU because you haven't moved to the GPU yet.
Even though, typically you would go to the GPU after a batch, but in this case he's saying, and I think he does touch on this.
It's still CPU.
It's still the CPU. That's what he's pointing out here.
In this one, I think this has to do with my runtime. It's the CPU because my runtime is
your runtime is CPU. Yes.
When I'm running on the GPU, which I didn't want to because then I exceed my limits. If I'm on a GPU, then my default device would be GPU. It's not that my default device is a CPU because I'm executing these in outside of the batch or in the batch. The device is what my runtime is.
Yes.
Exactly. But it's not running it's not reading what the runtime is, right? Saying. my A by default is going to be on the CPU.
Exactly. A by default is on the CPU. That's what I'm saying. Like, and then your default device is whatever you have, whatever your device is available, and GPU gets higher preference than CPU.
Got it. Yeah.
And
Exactly.
the point I was making was slightly different, which is that typically, and again, it goes through that in the in parts of it, typically anything you do, because one of the reasons to create the after batch transforms and then to make them all the same size, blah, 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 is typically after batch, you would want to run on the GPU. G as in graphics, meaning that you would, because you are batched, you want to execute it faster, typically. But in this case, he just says it's still on the CPU and he checks that.
Yeah, let's revise that once we see the next video. We can revise these assumptions. I think that's all we have for video number 2. We were only 11 minutes over time, so that's good.
No, that
any
was
other
very excellent coverage. I think it's very complex to go through so much.